All right. Hey guys, can everybody hear me? Okay. Okay, cool. So, yeah, so this review session is going to be on trees. So we're going to go through some slides that we have here. Also, this review session is going to be recorded too. So if you want to go back and watch anything, you will be able to. If you have any questions at any point throughout the review session, you can unmute yourself and just ask, or you could also post in the chat. And then we will do our best to answer all the questions. But yeah, okay, cool. So the slide linked here, we also have Python files, all the problems that we're going to go over. So if you want to follow along and write the solutions yourself, which we recommend doing, you should check out these links here. Cool. Okay. So to start off, so a tree is I guess maybe to give a general overview of what we're going to do. We're first going to talk about the abstract data type trees and then move into the tree. So to start with abstract data type trees, a tree is a specific abstract data type, meaning it's something that we've just defined for our own purposes. And it has two components to it, a label and branches. And the label is always the value inside the root node here. So for this particular tree, our label value is 10. And then the second component of a tree is the branches, which branches are specifically a list of trees. So if we look at this tree here, it has two branches. One is this branch here, and then two is this other branch here. And the cool thing about trees is that they're naturally very recursive because each of the branches are themselves a tree. So any function that we can call on the whole tree, we can call on any particular branch of that tree. And then also another definition, a tree with 0 branches is just called a leaf. Okay. So a couple other pieces of vocabulary here. Depth is just the distance from the root. So if you look at this picture here, I guess the root is at 0. And then anything the next level, this would be depth 1, depth 2, depth 3. And the height is just the maximum depth of the tree. Or you can kind of think about it as the length of the longest branch, which in this case would be here. So this tree's height would be 4. Okay. So we kind of talked about how we have this abstract data type implementation of trees. And with our abstract data types, we can break them up into constructors, which is basically what's actually what's actually creating the tree, and then selectors, which allow us to get information from the abstract data type. So for our tree, we have the tree constructor, which takes in a label, and branches. Note that branches has a default value of the empty list, meaning that if you want, it allows you to basically create trees without any branches, which are leaves, as you may remember. And so if you want to pass in branches, you can pass in a list of branches. Otherwise, you can just use the default value. In terms of selectors, we have a label select, which just returns the label, which is the value at the root node. And then branches, which will return the list of branches, which remember are trees. And then we also have another helpful function here, the isLeaf function, which returns true if the tree is a leaf, meaning that it has no branches, and false otherwise. Any questions so far? Okay, cool. All right, so here's just the code written out. I'm not really going to go through it. If you want to just look at it, we have it on the slides here. Cool. And here's just another example of how to construct a tree. So note, we just call the tree constructor, we pass in a label and then a list of trees as the branches value. And we can use the label and branches or selectors to pull information from the tree. We also can use isLeaf as well. So the interesting thing about the data abstraction specifically is that we can only create new trees. We can't really we can create them and kind of get the values from them, but we can't actually change or mutate them in any way. So if we try to do something like this, where okay, we construct this tree here, we pass in label, branches, and everything, and we try to set the label value to be 6 instead of 3, we'll get an error because you can't assign a value to a function call. So it doesn't necessarily make any sense to there's no way that we can like update the label value once we've constructed the tree. If we want to update the label value, we just have to create a new tree and pass in the new label value. So this is kind of motivation for why we use the class version of tree. Cool. Okay. So generally when we're solving tree questions, like I said, trees are very naturally recursive structures. So we'll typically want to take a recursive approach with tree questions. So when we solve recursive problems, we always want to start with a base. And remember that our base case is the smallest version of our problem, the simplest case, meaning where we don't have to do any additional work or recursive calls to get an answer. So for tree questions, typically the base case is going to be something involving like the tree being a leaf, because you don't really need to make any recursive calls on that tree because there's no branches or something like that. Typically for the recursive call, it works very well if we recursively call the function on our individual branches because they are themselves trees. So any function that takes in the whole tree can take in the branches as well. So that's typically, we resort to that. Yeah, so then normally we'll just put together the result from all the branches to get our final answer, depending on the question. And here are some kind of approaches that we normally take, maybe using max, min, sum, any, all. Or we could also create a new tree, because like I said, there's not really a way for us to mutate the tree without breaking the abstraction barrier. Okay, cool. So let's work on the first question here. So this is also on the Python file if you want to actually work on the Python file. Um, so implement the func path function, which takes in this tree, and maybe just to kind of explain this question, because I think this question is a little confusing. Basically, what we want to do is we have this like function that like, or this tree that like, where each of the labels is like an actual function. So looking at this example, the first, like the label value is basically like a function that adds 1. And then these two values are like the square function and then the cubing function respectively. So we have this tree T, and basically what we're going to do is like we pass in a number as well. In this case, that would be 3. And we're going to see if there's any way of using like any of these, like if there are any paths in the tree that will get us to 16 starting from 3 and using these functions. So I think there's some doc tests here. Oops. Okay. Go back. There's some doc tests here, but yeah, and they're also in the Python file. So take a couple minutes to work on that, and then we'll go through that together. Also, yeah, sorry, I forgot there's skeleton code for this. And when you finish, you can use like on the participants feature, there's like a yes, so you can like mark yes if you're finished.
And one more feature, if you're working on the Python file, you can go ahead and run the doc tests with this command for this question, and it should tell you if you passed the doc tests.
All right. Let's start going over it. Okay. So looking at this skeleton code here, it seems like this skeleton code lends itself very naturally to our traditional recursion with trees because we can see we have this if case here, which might be a base case. We have a for loop, and we're creating this paths and returning it at the end. So, okay. So maybe I guess like let's think about like going in order of the lines in this code. Let's think about what we might set paths equal to. So what kind of like what are we returning from this function? Like what type of object are we returning from this function? Open the chat. Yeah, okay. So I can see somebody answered list here. So yeah, we want to make sure that we return a list. So maybe a good thing to start our pass variable, like to set it equal to, would just be like some kind of empty list, right? And then we can kind of fill in paths as we go. Also, maybe another hint is the fact that we have this like paths.extend here. So, okay. Yikes. Transitions, yeah. So maybe let's start out and set paths equal to empty list. Okay, so now let's talk about the base case for this function. So, okay, oops, ignore that. Okay, so thinking about this, what is like potentially like the simplest case of function that we could take in for this? How do we know if we can like if we have like or I guess yeah, like what is like the simplest case of tree that we could potentially take in? Any ideas? You can also unmute yourself if you want. Yeah. So typically, when we do these tree questions, right, the simplest case of tree that we can take in is just a single node tree or just a leaf. Um, okay, so if T is just a leaf, then how do we know like if we have like a valid path? Like using that tree? Because there's only gonna be that means there's only gonna be one function within like our tree because there's just one node. So how would we know that we can get to end? If let's see, label T. Okay, so somebody in the chat said label T n equals n. T n. Yeah, right. That's yeah, because so if we call the value at the label on n, it should equal n, and then we know that would be a valid function. So yeah, so if we have a simple one node tree is leaf, and we can call the label value on n to get end, then we know we found a path. So in that case, what should we return? Any guesses? You can also unmute yourself and say it out loud too if you want. Okay,
List of
paths.
list.
Sorry.
A list of list containing the label.
Yeah, exactly. So I see there are a couple other guesses on here. We don't just want to return paths because paths is empty right now. We don't just want to return T because T is a tree. So we have to make sure that we return like a list with the label value inside of it. So yeah, we can construct that using, I guess like another thing that's important to note is it's like paths is like a list of lists because it's a list of all the different paths. So we have to like kind of nest this further in one level, like in another level of like brackets, because it's like we want one path in our list and this path just has one element. Any questions so far? Cool. Okay. All right, so let's talk about the recursive case now. So what so typically when we solve these recursion problems, right, we're looking for like, okay, a smaller subproblem that we can call our recursive function on. So what might be a good smaller subproblem? Like what input do we want to call our recursive function on?
So the branches in T?
Yeah, so we have this kind of for loop structure in the skeleton, and I can't go back without like clicking 25 times because of the transitions in here. So I'm just gonna leave it on the slide. But so yeah, we have this for loop structure here, and we know that like we are gonna like we're gonna like be adding stuff to paths, right? So there's a question here. How do we know when to use dot notation versus what we're doing here? Oh, great question. So yeah, the dot notation is used for the tree class. This is our abstract data type tree, meaning that like we should be using like the label and branches selectors. And actually, you can kind of differentiate between, like, this was something that I figured out when I was in the class. You can differentiate between the tree class and the tree data, the tree ADT, by looking to see if the T in tree is uppercase or lowercase. If it's lowercase, it's the ADT. If it's uppercase, it's the class. And then let's see, what is label TN doing? Yeah, exactly what Ethan said. So label T is a function, and so a function is going to get returned from this, so we're just calling that an N. Cool. Any other questions? All right. So, okay. So we need to like figure out how to like recursively like go through all the branches and like call this function on the branches. So what might be the, yeah, like, so we can do for B in branches, exactly. Okay. Yeah, for B in branches T. And then what should we do for each branch? We know we have to like recursively call our function, right? So what are we gonna like pass in? We need to pass in a T and N and end, right? Any ideas? You can either send in the chat or speak out loud.
Something involving a recursive call, maybe. I don't know. I haven't got that
Yeah,
far.
okay. Yes. So, well, since we, okay, there's an answer here. B label TN end. Okay, cool. So, right. So we know we need to pass in like a tree, an N value, and an end, right? And we need to make sure that like we have this like for B in branches T. So maybe it makes sense for us to put in B for T, since that's kind of like that's like the tree that we need to pass in, because we need like a smaller tree to pass in, since we're kind of working down our tree. And then yeah, we want to kind of update the value of N, because we need to be trying to get N to be closer to end. Sorry, I realize when I say N and end, it kind of sounds the same, but like, yeah, we need to be working the value of N towards the value of end to see if like, a path will get us there. So we want to like basically call the function at the label on N, but we want to keep N to be the same. So cool. Oops. Okay. So right. So if we find this, like, we have this recursive call here, func paths b label tn end. And if, like, I guess for any path that we get back in this list, because remember that func paths returns a list of paths, all we have to do, because these paths started from B, meaning that they're basically missing the label value, right? Because we kind of like called it recursively on like the branch. So we need to like add label T back into the path. And then at the end, we can just return paths.
I don't get why we have to return the label of T still, because like the results are just the functions themselves. Isn't the label of T the, oh, just kidding. That's a function too.
Oh yeah. So yeah, that's a great point. But yeah, just remember that func paths B, like all of the paths that are returned from that, they won't contain the label, because like the tree that you're like calling this recursive func paths on doesn't have the label inside of it. So you want to make sure you have the whole path, so you have the label back in. Cool. Any other questions? Okay, let's move on to the next question. Okay, so this is also on the Python file as well. So implement the lowest function, which just basically finds the label of the lowest depth. In this case, remember that depth is basically like the distance from the root. So in this case, it's 7, and if there's a tie, make sure to return the leftmost. Cool. So let me go to the skeleton code. All right, so take a few minutes to work on that, and then we'll go over it. All right, so I'm gonna start going over this question. Okay, so we have this helper function defined here, lowest pair. And there was a really good question in the chat that asked about like, okay, if we're doing lowest pair T0, isn't that kind of like breaking the abstraction barrier if we're assuming that like lowest pair T returns a tree? Because we don't really want to index into a tree, because we shouldn't be making the assumption that trees are like constructed using lists. So I think that's a really good indicator of maybe what type of object lowest pair T is supposed to return, right? We know we shouldn't be violating the abstraction barrier. So lowest pair T can't be returning a tree. So think about what other things we have that we're allowed to index into. So does anybody have any guesses about, yeah, okay, so there's a guess from Ethan. It says, yeah, we should return a list. Because yeah, if lowest pair T returns a list, then it's totally okay for us to index into it. Okay, so we know we have kind of our recursive setup here. So let's talk about maybe what a good base case for this lowest pair function might be. So we know we're going to return a list. What would be the simplest case of tree T that we could take into lowest pair? Yeah, a leaf. If we have a single node tree, right, there's no need for any recursive calls. We know that the lowest, I guess like the lowest hanging fruit in this tree is just going to be the label value, right? So, okay. All right. Yeah, so so if our tree is a leaf, what do we want to return? Knowing that we have to return a list from lowest pair. So we can't just return the label value. We have to structure it in some sort of list. Any guesses? Yeah, exactly. So if we just put the label of T in a list, label T0. Okay, that's interesting. I'm pretty sure this is actually okay to just do label T. So, right, because then what we can basically do, we know at the end, right, we're going to return the 0th index value from this function. So it'll just pull that label T out and return it. Cool. Okay, so now what do we need to do if, like, how are we going to handle our recursive cases? Oh, wait, we do need to have the 0? Let me check that for a second. T0. Oh, okay. Yes. Okay, that's my fault. My fault. Okay, so we do need the 0 because it's representing the depth at which this is at. Okay, my fault. I'll explain that, and once we go through the recursive part a little bit. But yeah, so we need to like go through Phrygian branches. So okay, so we have this here. So basically, if we okay, yes, okay. So what we need to figure out basically is like which branch is like the longest, right? So that we can basically pull the node value at the bottom of that. So what we can do to kind of help ourselves here is if we go through and call lowest pair for each branch, we can like use like, I don't know if you remember the key function for the max. That basically allows us to specify based on how we want to determine the max value. So in this case, the key is always like a 1 argument function. So this is basically taking in a pair and checking the value 1. And so this actually is why we need the 0 here, because what this is representing is like the depth in the tree. So if the tree is like a leaf, then the depth is just 0, right? Because there's no like distance between the label and this particular node, because the label is this particular node's value. So what we can do here is, wait, what does the backwards dash mean? Oh, the slash. Oh, that's just representing that this is just like the same line. We just put that in so that to represent that this is supposed to be part of this line. But yeah, okay. So if we basically call this lowest pair, right, we want to basically figure out, like, we get all of the lowest pair values from the branches, and we're going to check the depth values, which we've been storing at like the second element in the list, like index 1, and we were going to see which one is the largest. And that's going to help us determine which pair of like label and depth value is the one that's like furthest down. So that was a little confusing. So any questions about that?
I have a question.
Yeah.
Like, how is the depth value going to be building up? Because we didn't like build it up anywhere in this.
Great question. Yeah. So this isn't the full solution, so we have to do that as well.
Oh, okay.
But yeah. Right. Okay. Any other questions before I get into that?
Why do we need the key equals lambda pair 1 part? Because I was a little confused on that.
Yeah. So typically when we set the key function, it just means, because like, okay, when you take like the max or the min of like a list or like of anything, right? Like typically it's just like if you take the max of like a list of numbers, it's just going to pick the largest number, right? But the thing is like we're taking the max of like this like list of like pairs. So like it's like it has like a label value and like a depth. So it doesn't necessarily make sense how we would like take the max of that because it's just like a list of pairs. So we have to like kind of basically like say what we're using to compare the different pair values. So what we want to use in this case is the depth, which we're storing as the second element in the pair. So we have to put in this key function to show that that's how we want to figure out what our max is. Does that kind of make sense?
Yeah. Okay. Thank you.
Yeah, I think it also might maybe be helpful if we look at the next line of code too. Yeah, so then what we do here is we need to update the pair's depth, right? Because as we proceed back up the tree, the depth is like increasing by 1 each time. And at the end, we can just return the max pair because we've now adjusted its depth, so it's actually the correct depth within the tree, and we picked basically the pair with the largest depth by using this key function. And then we will just basically pull the label value, which will be stored at the 0th index of the pair. So any questions about the whole solution?
Hi, question.
Yeah.
And we usually don't use the key for max. And how can we decide if we to use the key?
Yeah, so you really need to use the key. Like what I said, maybe wasn't the most clear, but like you need to use the key if it's like, if you have something that's like more complicated than just like a list of numbers and you don't want to determine max just based on like, okay, straight up like number values or something like that. Like if you want to determine the max or min of a list based on like some specific attribute that may not actually just be like number values, you need to specify a key so that max knows how to like determine what the max actually is, right? Because like this like lowest pair B for B in branches T is a bunch of like lists of pairs, like these like 2-element lists, and each pair contains a label value and a depth. So it doesn't necessarily make sense how you would be comparing the different pairs, right? Because like, okay, the label value of the pair at like the greatest depth might be the largest label value. So do we want to like, pick that pair, or do we want to pick something like it doesn't necessarily make sense what you would like. There's no clear indication if you don't put in a key function of what you're going to judge based off of. Like, do you want to judge based off of the first value in the pair, the second value in the pair, the length of the pair? Like, I don't know. So that's typically why we want to use a key function. So if you're just taking like a max of like a list of numbers, you don't really need a key function.
Can you explain more about how pair bracket 1 works?
Pair. Okay, so basically, like the key function part.
Yeah, the input is pair. And
Yeah.
the
So
output is pair bracket 1.
Right. So the way that the key function works is it's always like a one-argument function, and it goes through each element in the list and like takes it in as like it'll like set it to be the pair value, and then it'll compare like based on like something here, whatever like this return value is. So what it's doing is it's basically going through all the elements, pulling out the second value in the pair, and then comparing all of them to see which one is the biggest. And then whichever one is the biggest, it takes that element, like whatever pair was, and returns that. Cool. Any other questions?
Yeah, how does the max pair of 1 plus equals 1 exactly work? Because we don't have any depths like while we're doing the max. So how does it like end up getting a depth before? You know what I mean?
So remember that like okay, so lowest pair returns like a 2-element list where like the first element is like some node value and the second element is like the depth that that value is at. So max pair, when we do like this like max, like the point of having the key is that it's going to pull one of the elements out of this list, like lowest pair B for B and branches T, and it's going to take that and like set that equal to max pair. So when we index into max pair at 1, it's getting the depth value and then it's just adding 1 to that. Does that make sense?
Yeah, thank you.
Okay, any other questions before we move on? Okay. All right. So we're going to switch over to Catherine presenting now.
Sorry, I was muted. Can everyone see my screen? Hopefully. Okay. So for the next part, okay, thanks, Ethan. For the next part, we're going to talk about the tree class. So I'm going to kind of go fast through this since, like Jade said, the tree class looks pretty much the same as the tree ADT, except the T is going to be capitalized and we're going to use dot notation. So for example, instead of isLeaf T, we'll call things like T.isLeaf. But otherwise, we still have label, we still have branches. They're just now going to be attributes instead of functions. Awesome, and this is what the tree implementation for the class looks like. So as you can see, the init method pretty much looks almost exactly the same as the ADT tree method. And we also have the attributes label and branches. One cool thing other than mutable trees we can do with the class is we have these repr and stir methods. So as you're testing your code, to see if the tree that you're returning looks right, you can go ahead and print the tree, and it looks a lot more like the normal tree structure than seeing like a bunch of nested lists, which is what you would see for the tree ADT. So this was the slide you saw before for the tree ADT, and here's just the same construction plus methods for the tree class itself. So we just see dot notation, branches is still a list, we have the label, and we can check if it's a leaf. And the full set of methods is in the Python file. And just like quick plug for people who just showed up, the slides link is links.cs6una.org/trees/slides. And please like download the Python file so you can follow along at links.cs6una.org/trees-files. No, it froze. Cool. So the reason we care about class trees is also so we can do a set of problems with mutable trees. So now that we have this tree class, as you've learned from OOP, you can use this dot notation to modify the attributes. Remember, the attributes we have for the tree are the label and the branches. So we can modify an existing tree such that the label is squared or the branches are doubled or something like that. And the general structure for mutable tree problems is actually not that different from normal tree problems. We still have the base case. Oftentimes, not always, it's going to be a leaf, where it's the smallest version of a problem. You're going to either mutate it or not mutate it, and then you'll be done. You also have the recursive call, where you're going to call this function on each branch of the tree. Typically, it's going to be a branch because you need to call it on some smaller tree, which is a branch. And then you have to put it together in the final answer, where sometimes, not always, you might mutate the root node. The branches should already be mutated through the recursive call at this point. Just one tricky thing I want to point out that confuses people is oftentimes these mutable tree problems are going to return none. So you might not have some like assignment statement such as b equals recursive call on branch, because this recursive call might just return none. So oftentimes you'll just see like a recursive call kind of plopped in the middle of the code. All right. Any questions on structure of class trees? I know that was kind of fast.
Can you explain one more time about you say return none?
Yeah, definitely. Okay, so
Thank you.
actually, let's just look at this problem, for example. So in this problem, it's going to be a mutable tree problem where we're going to return none. So see how in this problem, we take in a tree, T, and then we call remove nodes on T. This is a little ugly formatting, but you can see that nothing shows up after we call remove nodes on T, right? That means that it actually returns none. We actually know that the function is doing something when we ask the interpreter, okay, what does T look like now? And then we see that T itself has changed, but the function didn't return anything. Does that make sense?
Yes, thank you.
Awesome, no problem. And then one last thing before I start going over this problem is that the general strategy I use for mutable tree problems, and actually all tree problems, is I just go through all the branches. I saw someone kept saying in the chat earlier, always for V in branches. So oftentimes you're gonna loop through the branches, just look at each branch, ask if I recursively call my function on this branch, what is that going to look like? And then how do I combine it back together? All right, so this problem, just a brief introduction, we're going to take in a class tree, and we also take in a predicate. A predicate is just a one argument function that's going to return true or false. And then we're going to mutate the tree itself such that all of the values that satisfy the predicate are going to go away except for the root value. This except is really important. So as an example, if we look at this tree over here on the bottom left, once this bar goes away, we have this tree 1, 2, 3, 4, 5, 7, 8. And our predicate is this lambda x mod 2 equals 1, which is just odd numbers. And what we want to do is we want to just get rid of all of the odd numbers. So 7 goes away, the 5 goes away, but when we get, oh, sorry, I think I lagged out for a second. Am I back? My internet's pretty terrible. Hello, am I back? Hello? Can y'all hear me? Okay, cool.
Yeah, I think you're okay now. But yeah, you were like,
I'm sorry, my internet's terrible. And then for this last branch, what's important, this 5, which is also odd, we're going to get rid of this 5, but we're going to take all of 5's child branches and kind of like stick them back onto 1. Cool. Any questions on the layout of this problem? All right, let me go ahead and show the skeleton code then. So here's some doc tests. You can also try this on the interpreter and print it out, which might be helpful. And here's all the skeleton code. And I'll go over this probably in 5 minutes. Please mark the thumbs up button on the Zoom call under participants if you're done. And feel free to ask any questions. so heads up, I'm planning on going over this in about a minute, but if you need more time, please just say in the chat how many more minutes you need and we can spend that time. Okay, cool. Anyone want another minute before I go over this? Okay, if not, I'm just gonna start running through my approach. For these types of problems, I like to not jump into the code, but kind of formulate a game plan first. So like I said, my strategy for this is usually look at every single branch, assume we're gonna call it recursively, use the recursive leap of faith, figure out what the recursive call is going to do to each branch. Remember here, the recursive call isn't returning anything. So I'm kind of just gonna ask, how is my recursive call going to change each branch? So I just drew out an example here. It's not the same as this one, but if I were to pass in this tree, I want my final result to look something like this. I'm just getting rid of all of the odd numbers except for the root. So remember, this question is saying if I call it on a tree, I'm going to get rid of all of the odd numbers or the labels that match this predicate except for the root. So recursively, if I call this function on 2, this is just going to give me back 2 because 2 is not odd, it's just a label, that's just what's going to happen here. Okay, this one's kind of tricky. Can anyone tell me how this branch 3, 4 is going to change when I just go ahead and call remove nodes on 3, 4? In other words, like what would Python display? Remove nodes 3, 4. Anyone have any guesses? Okay, and says it'll compress to just 4. That's what we want it to do, but this is kind of tricky. If you remember the question, it actually says it's going to, it's not going to return anything, but it's actually not going to change this branch when we call remove nodes on 3, 4. Remove nodes of 3, 4 is actually going to keep it exactly the same with this predicate because it's not going to change the label. So I think this is one of the trickiest parts for this recursive leap of faith. This is actually not going to change at all. In order to get rid of the 3, that's going to happen after this recursive call. That's kind of weird. So this next branch, I'm just going to like change this tree as we go. This next branch 4, 9, this one's going to change because 9 is not the label value and it's odd. So when we call it recursively on this branch, we're going to ax the 9. And for this branch, weird again, the 5 is going to stay here, but the 7 is going to go away. So keep in mind the question, we're only getting rid of values that are not the root that match this predicate. Cool. That was kind of weird. Any questions so far on that step? Okay, I'm going to write that into code now. So what we did is we're going to, why didn't the 3, 4 branch change? Question. So essentially what we're doing in the recursive call is we're not going to get rid of any of these label values. When I call remove nodes on the tree 3, 4 with this predicate, I'm not going to get rid of the 3. Because the question, actually, let me just go back a slide. Go back several slides. Here's the question. It says that we're going to remove all the nodes excluding the root node. So if we recursively call it on 3, 4, then 3 is the root node and we're not going to get rid of 3. Does that make sense? We're going to get rid of the 3 in the next step. Okay, so just writing out what we've done so far, we've looped through all the branches for B and T dot branches. And we've kind of just like trimmed everything below the immediate branch level. So if this is layer 0 or depth 0, this is depth 1, we've kind of just like trimmed everything depth 2 on. And we did that by calling recursively remove nodes on each of the branches with the same predicate. Excuse my bad handwriting. Okay, so I feel like there's some confusion, like what the heck, we're not at the answer. This is wrong, there's a 3 and a 5 here. So now what we need to do is, remember, our recursive call trimmed everything from depth 2 onwards. It got rid of all those. But now we have to deal with this depth 1, this branch level. We need to get rid of the bad ones here. Okay, so how do we know if we want to get rid of something? Well, we'll just call the predicate function on this value. So here, our next step is going to be, we're still looping through the branches. So for this branch, if b.label, we look at b.label, if that satisfies the predicate, I should have left myself more space here. Let me rewrite that. So if b.label satisfies the predicate, which we can check with pred of b.label, that's, for example, this 3, then we actually want to do 2 things, right? The first thing we want to do is we want to get rid of this branch. I don't want 1 connected to 3 anymore. So I kind of want to get rid of this branch, but I also want 1 to connect to 4. So as you can see down here, we kind of like steal 3's branch, and we want to draw a line over here. So those are kind of the 2 steps that we want here. And what that looks like is, recall that branches is just a list. So in order to, first off, kind of steal 3's branches, what we can do is we can just call t.branches.extend, which adds on to my list of branches all of this b's branches, b.branches. And what this looks like in terms of the code is, currently my branches are something like this, 2, 3, 4, 5, where this 3 is this 4. And this b's branches is a list with just 4 in it. So when we extend my branches with b's branches, I'm just like sticking on the 4 onto my branches list. And then finally, I want to get rid of this 3 branch, like that line that I erased. In order to do that, we can just go ahead and call t.branches.remove of b itself. And so that does our 2 steps, where for each branch, if its label is bad, if it satisfies the predicate, we get rid of it. And we also steal its branches. Is the extend method, yeah, it's not built into the tree class, but here, see that we have t.branches.extend, where branches is a list. So we can do that. Cool. Yeah, this question is kind of hard. Any questions, points of confusion? And also, I know we went through this kind of fast. Isn't that breaking the abstraction barrier? So we're allowed, t.branches always is a list. That's just given to us. What we can't assume is, we can't assume that t is a list, which it's not in this case. This is also a nice thing about classes. We can't really break the abstraction barrier because there is no abstraction, which is cool. All right. And yeah, this was kind of fast. So if you're feeling like completely lost or anything, I'm also going to stick around after the call. Feel free to ask more questions then. All right. So that's the strategy, by the way, I'm going to be using for all these problems. And just to check, here's the solution. Oh, yeah, question?
Sorry to disrupt you, but as a quick question, could we go over that strategy one more time? Could you just repeat what you said would be good to do for your strategy?
Yes, definitely. So my strategy, let's just think of like some arbitrary tree and arbitrary question, is, like Jade said, tree questions are typically recursive. It's not a huge leap to assume we're going to use recursion. For a function, I'm going to assume we recursively call it on each of the branches, draw out what happens. I always draw pictures for these. Draw out what happens to each of the branches when we make the recursive call. So that was like the deleting the branches from that previous picture. And then seeing, all right, what else do I need to do from here after I've recursively called on all of the branches to build back into my goal return value.
Okay. So that's additional things that we need to do when we're going throughout our pieces, is we need to assume that we're going through we assume look at what's going on with the recursive call in the branches. We should draw out what happens, and we should practice drawing out the tree so we're ready to go. And then we need to figure out what else we need to do after the recursive call.
Exactly. For non-mutative tree questions, I just like draw out what each of the branches turns into. It might be turning into another tree, a number, and then just like see how do I combine these parts to come back together. And typically that works out.
All right, thank you.
Cool, yeah, no problem. I'll do that for the next question. Oh yeah, question.
Yeah. So my question is, why do you have extend? Shouldn't it be append? Because you know.
Oh, that's a good question. So remember, b.branches is a list, right?
Yeah.
So extend takes in a list and kind of like smushes it all together, so it's a flat list. If we append a list, then what t.branches is going to look like is it's going to have like some trees and then it's going to have another list in t.branches. But we want t.branches to just be a list of trees, not a list of trees. Does that make sense?
Yeah, sure.
Okay, cool. So the extend version, if we extended this list, would look like this, whereas if we append this list, would look something like this. So we just don't want nested lists. Cool. All right. So I think we're a little low on time, so I'm gonna go over this question at the end. If we get time, look away real quick as the solution shows up for a second. Okay, I'm gonna go over this because I think it's a little more challenging. Okay, so here's the question. It's another immutable trees question. So implement the function maxify, which is going to take in a tree with integers. So all of the labels are going to be integers, like that. And it's going to turn it into a max tree, where a max tree is defined where the root value needs to be bigger than all the values below it, and also each branch is a max tree. So that's kind of confusing. So just running through a quick example, this first case, if we have the tree 1, 2, 3 over here, in order to maxify it, and we want to keep the same like label values, we just kind of want to reorganize them a little bit. What I need to do is I need this 3 to go up here. So a max tree would look like 3, 2, 1, because 3 needs to be the largest value. And you can similarly run through the example for T2 down here, where we're going to maxify it. Let me run through it just because this question might be a little confusing. So for T2, we have this 5, 2, 4, 3, 6. Okay, so there's a lot of things wrong with here. The first thing is 6 needs to be at the top. We need each branch to additionally be a max tree. So this needs to turn into 4, 2, 3. So this needs to turn into this. And this doesn't return anything. It's just going to mutate the tree. Cool. There's also several possible answers for each max tree. All right, so here's the skeleton code you're given along with the dog test that we had. Okay. Oh, sorry. All right, cool. I'll give you all another 6 minutes to work on this. If you're done, press the thumbs up button. Okay, I'm gonna start going over this problem. Does anyone want another minute to try this on their own? Okay, this problem's kind of hard, so as usual, please feel free to like unmute yourself or message in the chat if something's confusing or I can elaborate on something more. Cool, so I'm gonna go through the same strategy that I mentioned before for solving this problem, where I'm given this tree, I want to mutate it. I'm kind of just going to ask, well, what if I call it on each of the branches? How is that going to change? And then I'll see how to put it all together again. We have some skeleton code. If it's a leaf, we're already given, we're just not going to really do anything, right? Because if I give you any leaf, no matter what's in it, that itself is already a max tree because there's nothing below it. It's the largest value in the entire tree because it's the only value. So we're just going to leave it alone. Next, for B and T dot branches. All right, here's a good time to try to figure out what my recursive call is going to do to each of these branches. I'm working on the second example, T2 over here. So here's my first branch. This is kind of the interesting branch. 2, 4, 3. Okay, so instead of asking you to write out what this is going to look like if we recursively call, I just want to do a quick check. Can people tell me if this is also a valid max tree? 3, 4, 2. Anyone know? No, exactly. Vanessa says no. Yeah, so we can see that this is not a valid max tree. In other words, we cannot swap 3 and 2 because 4, the largest branch value, needs to be at the top. So essentially what we're going to do for this problem is we're just going to swap around label values. We're not going to change nodes or branches. We're just going to swap label values. And here, to put into words what happened here, this will come in handy later, we essentially just like take in the largest branch value and swap it with the root. Cool. But for now, all we're doing is we're using the recursive leap of faith. So using my recursive leap of faith, I'm going to say this 2, 4, 3 is magically going to turn into the max tree version, which is going to be, as we see down here, 4, 2, 3. So essentially, I'm just going to swap this 4 and the 2 using my recursive leap of faith, and we're all good. 6 should just stay a 6 because it's a leaf. Nothing really happens. That's what we see here. Well, now that I've done that, you might notice, well, I'm not done. Let's just write that down on the code first. First step for B and T dot branches, I'm going to go ahead and maxify B. So there's a question earlier on like, what do I mean by it returns none, don't assign it to anything. We just kind of have this recursive call out there. It's going to mutate it. We don't assign this to anything. Just going to maxify it. All right. Now we have this line over here. It's like weird max thing where we're trying to find this int. I think on the skeleton code actually says index to make it a little clearer. So based on this context clues, we might assume this is some sort of index. In fact, it's an index into one of the branches. And at the end, we're going to maxify this index into the branches. So now the question is, how do I get from this tree to this tree? Well, like we figured out before, we're going to do a label swap. But the swap we need to do has to be swapping with the largest label. So 5 can't swap with 4. It's going to make things even worse. 5 needs to swap with the largest label out of any of the branch labels, which is 6. Let me know if I've lost you on that wording there for anyone, because that's going to be kind of hard to translate into code actually. So what we're doing is we're looking over all of the branch labels, right? So here we have 2 branch labels. We have 0 and 1. So for example, here we might have 0 and 1. And we want to select the index whose corresponding branch is going to have the largest label. All right, so let's do this like max with the key thing all over again. So what are we taking the max over? Well, we're looking over all the possible indices of the tree branch indices. So in other words, that's going to be a range from 0 to the number of tree branches. So the range of the len of, oh, this is kind of hard to squeeze in, T dot branches. So what this means is if I have like 5 branches, that's going to give me 0, 1, 2, 3, 4. If I have 2 branches like here, I get 0, 1. I'm going to select the max out of those. I don't just care about the largest number, right? That's where the key function comes in. I care about the index that corresponds to, probably going to go over this line here. Let's say this is the number. So that corresponds to the branch with the largest label. And putting that into words, it's going to be T dot branches of X. So I'm selecting the Xth branch dot label. All right, so here's another usage of the key function. essentially I'm going to go over 0, 1. I'm going to ask, what is the 0th branch's label? It's 4. What's the first branch's label? That's going to be 6. And I'm going to select 1 because 6 is the largest out of these. Any questions on that line? That was also a lot of stuff.
What happened in the drawing after the recursive call when we were going through it? And then how does the inline make an impact on that? Because I got a little confused when I went through it. Because I was just going to the base case and returning none for the recursive call. Wouldn't that do nothing to the tree when I was going through it?
Good question. So on the base case, you're right. We're doing absolutely nothing in the base case. But we'll see that this maxify is actually going to do things. The first explanation is we're going to use the recursive leap of faith that it's going to work. But the actual explanation is if you see once we get to line 15, we're actually going to change values. So that's where the magic is happening. So maxify is actually changing it. So in the drawing, what happened is it went from 2, 4, 3 into 4, 2, 3.
Okay, so we're assuming it works using those values. And then the end, why are we going for the max of the range of the length? And then we're doing the lambda x with a list of the branches and then using the dot label.
Yeah, good question. One small thing, this code could actually probably be cleaner if we didn't look at the index, but the way the code is laid out, we're trying to find the index of the branch that has the largest label. Does that goal make sense?
Yeah, that part makes sense.
Yeah, so then in order to do that, I have to ask, what are all of the possible indices? All of the possible indices is represented by the range of the len of t dot branches. Len t dot branches is just however many branches I have. Calling range on that is just going to give me all the numbers. So like 5 branches, I get 0, 1, 2, 3, 4.
Okay, cool.
And then finally, this is just like kind of complicated for say, figure out which branch using like this indexing has the largest label.
Okay.
Okay.
Okay, cool. All right, thank you.
Yeah, no problem. So now that we've gotten that index, what we're going to do is, well, in this case, I first need to check, is t dot label even smaller than this label? If this 5 were like a 7, we would just be done, right? There's no reason to swap the 7 and the 6. But if t dot label 5 is less than the maximum label, which is what this is representing here, then we need to go ahead and swap them. So here we can just do like a one-line swap, where I can say t dot label, comma, t dot branches int at that index dot label, again, a very long line, is going to be equal to just the swap. I'm going to swap it. So t dot label is now going to be t dot branches int dot label, comma, t dot branches int dot label is going to be t dot label. And that's going to do my final step, where finally this 5 and, oh, that just went away completely. This 5 and the 6 are going to be swapped. Cool, and that gives me my final answer. Oh wait, sorry, that doesn't give me my final answer. That gives me the final answer for this problem. But then there's also the problem of what if there were more values down here? So for example, what if down here there was like that's impossible, but if there was like a 5.5 or something that's in between these values, we need to make sure that after the swap between these two numbers, this branch is still going to be a max tree. So then finally, I'm going to use the recursive leap of faith again. I'm going to call maxify on this tree that I just changed all over again, so that these numbers can change around. And this will, using the recursive leap of faith, make it so that those two numbers are going to change. And then I'll get finally like a valid max tree. The dog test didn't really show why this is necessary, but we need to do that in order to make sure that this branch we changed is still a valid max tree.
Oh, Catherine, I have a question. Yeah, but I do not understand the necessity for the last maxify.
Yeah,
Because
good question.
by a definition, won't the maxify of B in the for loop take care of that?
That's a good question. So let me draw out a quick example that might show the necessity of this. Let's see, sorry. Okay, so let's just look at a quick tree. Let's say we have 1, 3, and then 4 and 5. Okay, let's say we have this tree, right? So running through how this code is going to work, I'm going to recursively maxify each of the branches. 3 stays as 3, 4, 5 turns into 5, 4. Then I'm going to swap the 1 and the 5. Feel free to stop me if at any point it's like went too fast. I swap the 1 and the 5, 5, 1. This is not a max tree, right? This is a problem right here, because a max tree by definition, each branch is a max tree, but this isn't. So I need to recursively turn this branch also into a max tree. So that's where this line comes in handy.
Oh, I see. I see. Okay.
Yeah,
you
sorry
swap
the first case didn't really show that. But
Thank you.
cool. Any other questions? Ran through this kind of fast. All right, cool. In that case, let's just go over some final tips. There's the solution. It's also on in the files, the solution.py. Okay. Is it not? Oh God. Okay. So final tree tips. As you've seen from a lot of these questions, base case, oftentimes we're going to check, is the tree a leaf? There's also questions where there are other conditions, such as looking at the label of that tree, or like in the first question Jade went over, if the function of the label is a certain value. Recursion, trees are recursive, which means each branch is a tree, which means you probably need to do tree recursion because iteration on trees is almost impossible. So oftentimes you'll see for B and T dot branches or a list comprehension over each for B and T dot branches, just try to figure out what is the recursive call going to look like, and then finally put it together. And then for mutation, just always figure out, quick rule of thumb, if you're returning none, you're probably doing tree mutation. But overall, still the same strategies. Ask if I recursively mutate the branch, what's going to happen, and then what else do I have to change after mutating all of the branches. Cool. And yeah, that should be it. Good luck on any tree questions and any questions you'll do on the final, and thanks for coming. If you have any questions about any of the problems, no problem. Feel free to ask. I'll stick around. Yep, thanks for coming.